The next few examples, we're going to look at analyzing the location of the vertical and horizontal asymptotes and the x-intercepts in further detail. They give you a key concepts box here that helps you analyze the information. This is the same information that I gave you in the first video of this lesson, where we're looking at the related zeros. Any factors that are in the denominator will end up being related back to vertical asymptotes. So if you have a factor in the denominator, that factor and its related zero will then tell you location of vertical asymptotes. There's also a conversation here about the horizontal asymptote with the location of those, and the m and n represent the degrees of the polynomial. So you can see that n is a degree of the polynomial in the numerator, m is the degree of the polynomial in the denominator. So if the numerator is less than the denominator, then you have a horizontal asymptote at y equals 0. So anytime the denominator is a bigger power than the numerator, you will always have a horizontal asymptote at 1. If those degrees in the numerator and denominator are tied, then you will have a horizontal asymptote at the ratio of their leading coefficients. So the a sub n and the b sub m represent the coefficients of your leading term. So you write the ratio of the leading coefficients of the terms when the degrees are tied, and you'll know the location of your horizontal asymptote. And there is another case where if your numerator has a higher degree than your denominator, then there is no horizontal asymptote. It is technically called an oblique asymptote, and we'll visit about that later on. I think I previewed that in the first video as well. The x-intercepts and the y-intercepts, we are very familiar with how to find x and y-intercepts. We'll plug in a 0 for the y in order to find the x-intercepts. In order to find the y-intercepts, we input or substitute in for all the x values as 0 for x, and that'll help us find their y-intercept. They give you a step-by-step directions in here and how to do that as well. Those are some pretty good suggestions, but let's take a look at the first two examples where they're telling us that n is less than m and n is greater than m. So these are the two different varieties they want us to look at this point. So for each function, determine any vertical and horizontal asymptote that intersects, then graph the function status domain. What is always helpful with any of these rational functions is to make sure that you have both your numerator and denominator in factored form. In the denominator, we can factor this so that we can have an x plus 3 and x minus 1 in factored form. When it's in factored form, it shows you the information about vertical asymptotes and domains much easier. So this form is an advantage whenever you're trying to find restrictions on the domain. And on that, we're going to make sure that our domain is restricted so that we don't divide by 0. And using set builder notation, that means x could be an element of real numbers, such that don't let x equal a negative 3 or a positive 1. So our domain has been restricted. Our vertical asymptotes are in the exact same locations. Where we had our restrictions in the domain, we can't divide by 0. That will also tell us what and where the locations of our vertical asymptotes are. So what are the related zeros to these factors? And that is when x is a negative 3 and when x is a positive 1. So we have two vertical asymptotes in this graph. We're going to investigate the horizontal asymptotes. The horizontal asymptotes is a matter of degree. This is a 0 degree or 0th degree polynomial at the top. There's no x value, so we just call that a degree 0. On the bottom, it's a 2nd degree polynomial. So this is the case where the denominator has a larger degree than the numerator. Basically what's happening is this dominant term, the x squared, is growing much faster than the 2, which is a constant. So as the x values get larger and larger, as x goes to positive infinity, the denominator takes on larger and larger values. And as soon as the denominators get large and your numerator stays virtually the same, it's going to stay 2, your fraction gets closer and closer to 0. So the bottom line is anytime your denominator has a larger degree, that means your horizontal asymptote is going to be located at 0. So when y equals 0, that will model the end behavior of this graph really well. The next two concepts are the intercepts. So to find the x and the y-intercepts, I'm just going to go over here to our x and y-axis for quick reference. Anytime we find an x-intercept, we know that we have an x value, but we are guaranteed that our y value is 0. So in order to find the x-intercept for this graph, what I want to do is I want to force the y values, or the outputs, to be equal to 0. So that means I want the output, h of x, to be a 0. And what is the input that can create an output of 0? There's only one way that this can happen. With any fraction, just generalizing a over b, the only way a fraction can equal 0 is if the numerator is equal to 0. So is there any value that we can put into this numerator that would force an output of 0? And that means, can we make a 2 into a 0? And that's not the case. So what that tells us is that there is no x-intercept. So there shouldn't be any crossings of the x-axis on this graph. Then we're going to find the y-intercept. The y-intercept, just generalizing over here, anytime you have a y-intercept, you know that your x value has to be 0, then you can find the y value. So what is different in this strategy or in this thinking is, what we want to do is we want to substitute in for x zeros, and then we can find our y. So we're going to find our h at 0, which means we're putting in zeros for x. And it's going to be 2 over, then it's 0 plus 3, and 0 minus 1. So it's going to be 2 over, this is a 3 times a negative 1, or a negative 3, so it should be a negative 3 halves. Or, I'm sorry, negative 2/3. So our y-intercept is at the ordered pair 0, negative 2/3. So I think we have all the required values that they want us to have. Now we're going to go into our sketch. Throw off a little space here. And increase the size of the x and y axis. Okay. First thing we do is we put in the location of the two vertical asymptotes. There's a vertical asymptote at negative 3, so we've got 1, 2, 3. We're going to drag one over there. There's a vertical asymptote at 1. So that's what these are located here for. So vertical asymptotes at a negative 3 to positive 1. These are the lines that your graph should not touch. They'll come close to but never touch. The other one that we want to place in there is our horizontal asymptote, and that's right on that x-axis. So I'm going to extend that out. Now, typically we talk about asymptotic behavior. Your graph can't touch them. Well, on a horizontal asymptote, the horizontal is here strictly for end behavior of our graph. Our graph may, it doesn't have to, but it may cross a horizontal asymptote more or less in the middle of our graph. So it may be crossing somewhere in these regions. It's okay if that happens, but what you can have happen is you don't want to touch your horizontal axis out towards the end behavior. So, you know, we've got our horizontal asymptotes in, we've got our vertical asymptote in, we've got a y-intercept at 0, negative 2/3. So if this is a negative 1, negative 2/3 is going to be in this location. And now to get the behavior by the vertical asymptotes, what I do is I choose a value that's relatively close to one of the vertical asymptotes, so I'm going to put in a 2. And I want to see what kind of numbers am I going to get. I know on vertical asymptotes it has to be approaching either a positive infinity or a negative infinity. And my job on this is just to use some sign analysis to determine, are the values positive or negative close to this vertical asymptote. So I'm going to choose a 2 and I'm going to plug it into our equation. So it's 2 over, and I just need the signs, but I'm going to put in the numbers here. It's 2 plus 3, which is 5. And 2 minus 1, which is 1. So you can see that we're going to get a positive number 2/5. As we get numbers closer and closer and closer to the vertical asymptote, these numbers will just become larger and larger positives. Now when I talk about sign analysis, what I mean is I don't have to write down anything other than the signs of our numerator and denominator. So again, coming back up into this, using just the analogy of sign analysis, that 2 is a positive number, so I just want a positive on the top. If I take 2 plus 3, it's going to give me a positive number. It's positive 5. I don't care. It's just positive. 2 minus 1, that's going to be a positive number. So what we're going to end up looking at is what happens when we take a positive divided by another positive number. Well, they're always going to be positive. So this one's coming from positive infinity. It doesn't have any x-intercepts that we can use. Then we want to go towards our end behavior, towards our horizontal asymptote. The other behavior that we normally see along vertical asymptotes, there are some exceptions, we'll cover them when they come. But typically, if it's on the right side, it's going towards positive infinity, then on the left side, it should be coming from negative infinity. Like I said, there are some exceptions to this rule, but we can use sign analysis to show that it is coming from negative infinity. But typically, you'll see opposite behavior on a vertical asymptote. And the other thing that kind of tells us that is we have a landmark to get. There's a y-intercept here. So we're going to come from negative infinity, go towards our landmark of our negative 2/3 for our y-intercept. Keep in mind, there are no x-intercepts on this graph, so our graph can't touch or cross the x-axis. So it's going to have to make a turnabout here and come right back down towards our other vertical asymptote. So it's going to approach a negative infinity. If it's approaching negative infinity on the right side, then on the left side it should alternate and should be coming from positive infinity. So it's coming from positive infinity. There aren't any other landmarks to hit except for the fact we want to flatten out towards our horizontal asymptote. So this should be a pretty good fit for what this graph looks like. We're going after the general appearance. I don't want you all concerned about the behavior in here. I don't care if you do this and it flattens out a little bit faster. What we have is the general shape of the graph. So 2A is finished. Let's take a look at 2B. We'll need those again. I'll just slide them off away out of the working section of our whiteboard. So first thing I want to do is I want to take function n of x and I want to rewrite it so it's in factored form, so it's x all over, and this is going to be an x plus 2 and x minus 1. Okay, in factored form, it's easy to retrieve a lot of information, such as a domain. The domain can be any real number except where the denominator is equal to 0, and that means x can be any real number with some exceptions. The related zeros, so that means x cannot equal a negative 2 or a positive 1. The vertical asymptotes mirror that same idea of the domain. The vertical asymptotes are located anywhere or for any value where x is going to create a 0 in the denominator, so when x is a negative 2, and our second one is when x is equal to a positive 1. The next thing we'll look for is horizontal asymptote. In order to find the horizontal asymptote, it's a matter of degree. This is a first degree polynomial all over a second degree polynomial. Anytime the bottom is larger, the horizontal asymptote is going to be at 0. Okay? Bottom is going to grow faster than the top, and anytime that happens, the bottom of the other fraction is going to be larger than the top, which means it's approaching 0. The next thing that we're looking for are both the x and the y-intercepts. So the x-intercept, when we grab an x-intercept, we know that we need to put a 0 in for y and solve. So really what I'm doing is I'm thinking I need this fraction to end up equaling 0. The only time a fraction equals 0 is when the numerator is equal to 0. So really I need the zeros of the numerator in order to find the x-intercept. Well, x is the numerator. The only way that x can equal 0 is when x is a 0. So that means we have 0 for x for an input, and we get a 0 back out for our output. So our x and y-intercept should both be at the origin. And we can see this probably repeated if I go through the analogy. If we're going to find our y-intercept, you have to put a 0 for x. And as soon as you put in a 0 for x, you know that your numerator is 0, your denominator is just a negative 2, and 0 divided by negative 2 is 0. So basically when it crosses the origin, that will be your x and your y-intercept. I believe that's all of our required data that we need. So now we're going to start placing our asymptotic behavior in. So this is negative 1, negative 2. This is at a positive 1. Sliding our vertical asymptotes over to match that concept. We also said our horizontal asymptote was at 0, so I'm going to put that back on the x-axis. We have one crossing of the x and the y-axis. It's at the origin, so I'm going to put that point in there. And we have all of our basic building blocks of our function that we need to graph. So again, I have a vertical asymptote at 1. I'm going to test a number close to it and look at some sign analysis. If I put in a 2 for x, that's going to be a positive 2. If I put in a 2 for x, that's going to be a positive. 2 plus 2 is 4. Then I'm going to put a 2 in for x. That's positive again. And it happens that we got a positive divided by positive. So we're coming from positive infinity near this vertical asymptote. That's the reason I chose 2, because it's on the right side. So on the right side of the vertical asymptote, it's coming from positive infinity. There are no x-intercepts out here. I'm just going to approach the horizontal asymptote. The behavior by these vertical asymptotes is typically alternate behavior. I didn't do it on the last one, but I'll try it on this one. What is a number that is relatively close to a 1? And I'm going to try a half. All I need to know is, are my signs going to be positive or negative? So if I put in a half, that x is going to be a positive. If I put in a half plus 2, that's going to be a positive number. But if I put in a half and subtract 1, that means it's going to be a negative. So negative. So I really have a positive number divided by a negative number. So when we get to this left side of this vertical asymptote, we should be coming from a negative infinity. And that's where that alternate behavior comes into play. So it alternates. We have a landmark to hit. We'd have to go through the origin. So now we have to head towards the next vertical asymptote. We cross through the origin. We're going to head right back up towards our other vertical asymptote. If you have any doubts about what this graph is doing, then what you can do is you can come back and do another sign analysis close to a -2, so I would choose something like a -1, plug it in for x. If I put in a -1 for that x, that would be a negative sign. If I put a -1 in for this factor, I'd still get a positive number, because any number between this -2 and 1 is going to give you a positive. And then if I put in a -1 and subtract 1, that's going to be a negative. So we got a negative on the top, and we end up with a positive times negative, which is a negative on the bottom, which ends up giving us a positive infinity. So it's going towards positive infinity, which is kind of where I've already drawn this graph. So using that sign analysis can help solidify that you draw the graph correctly just based on the behavior by the vertical asymptote. So because it's going to positive infinity on the right side, it should alternate and come back as a negative infinity on the left side. Then it's got to come up and flatten out and get close to your horizontal asymptote. Okay, so sketching rational functions using your horizontal, vertical asymptotes, x and y intercepts, and the behavior surrounding or close to those vertical asymptotes by sign analysis.